Hi folks, I'm Vanessa Sockett. I'm a principal computer scientist at Lawrence Livermore National Laboratory, and I hope you're excited because I like to qubit. You like to qubit! Indeed, today we are talking about the new integration with Flux Framework and the Kubeflow Trainer. Let's get started. So if you've never heard of Flux Framework is the workload manager that's developed at Lawrence Livermore National Laboratory. What makes Flux special is that it combines hierarchical job management with graph-based scheduling. So what does this mean for Kubeflow? It means that you can combine simulation with your AI ML workloads. For example, if you have an AI ML model that is informed by more traditional HPC scientific simulation, for example, something that uses MPI, the message passing interface, this integration will be of interest to you. And so what Flux adds that's special is a ZeroMQ bootstrap instead of a traditional SSH bootstrap, which is a little bit complicated with having the credentials and kind of the launcher and worker design. It also adds support for many more variants of MPI and also PMIX, the process management interface. What makes Flux special? Let me tell you the ways before we jump into the demo. So Flux runs on big computers. Specifically, this means El Capitan, the #1 supercomputer in the top 500 list for 2 years in a row. Flux also enables converged computing. We run it on cloud VMs. We, of course, run it on traditional HPC. Kubernetes, user space Kubernetes down to a single container. Flux is also analogous to Kubernetes in that it has a modular design. This is in contrast to many HPC software stacks that tend to be kind of monolithic and huge. Flux affords elasticity and dynamism, so when you create a cluster in Kubernetes, it can grow and it can shrink. Flux also, it basically has a scheduling design that's really neat. The hierarchical scheduling breaks traditional monolithic designs. So specifically, you can have scheduling decisions that are distributed at multiple levels, decisions and policies. You can manage resources and optimize them at each level. This is something that does not work well or maybe not even be possible in traditional Kubernetes. And finally, it enables system research and innovation because you can grab one of those components and develop it and then plug it back into your cluster. So with that, let's jump into the hands-on tutorial. Alrighty, let's get started. So let's look at the cluster that we have. We have 2 nodes, the HPC-6A that are running on AWS. This is notable because we're going to be using EFA, the Elastic Fabric Adapter, for improved networking. So the first thing that we want to do is install the trainer. I'm going to install it directly from GitHub from the master branch because I like to live dangerously. Once we install the trainer, then we need to install the Flux runtime. So let's take a look at that very quickly. We have it right here. So here we have, this is a cluster training runtime. And really what's important here is that we set the ML policy to Flux. Now under this, you can set a default number of processes per node, but we're just going to leave it blank because we're going to use the default. And actually, we're going to be setting that in our train job. Let's look at our train job. So this train job, this is a train job. We're going to call it lamps flux. Here's that important connection. We are using a runtime ref by name Flux runtime. That's the one that we just created and we've looked at. For the trainer, this is where we're setting the resources. So we're setting the number of nodes to 2, and the HPC-6A type has 96 processes per node. Now for our image, we're going to use a lamps image that is built with something called libfabric. We need that specifically for EFA. Here's our command. So lamps, the executable is LMP. Now, a lot of MPI orchestrators in Kubernetes require you to write like MPI run and to figure all that out. You do not need to do that here. You just need to put your application command. The Flux integration is going to add the wrapper to it, and we'll see that a little bit later. Now, we also need to add resources per node, specifically limits and requests for VPC, Amazon, AWS.com/EFA, one device. and we're going to kind of customize the EFA or optimize it for use in the environment. So specifically this variable, and the 5 provider set EFA. Flux can also be customized via environment variables. So for the Flux view image, we're going to basically change the operating system and version by way of this container image. Specifically, we want Ubuntu Jammy. Okay, so how about we make that train job, shall we? Let's apply it. It will be created. So we can do kubectl get pods watch. When it's a knitting, that is installing Flux via an empty directory to your container. The pod initializing step will be basically mean pulling the container. We already pulled it though, with a little bit of cheating. So let's take a look at the logs for the lamps Flux node 0. 0 if the lead broker is running the simulation. So here we have some Python versions, root, the command that you provided, the flags for Flux. And here's the Flux wrapped command that I mentioned. And here's the command that we provided here. Now lamps is running. The way it's going to run here is it actually runs and then spits the output. That's just for this particular build. And so let's go back up to look at a few things. So this is the main lamps running. This is kind of the start up here when you see this little print. Then here's the main running. It'll basically print 1 line for 10 time steps. Now, if you're interested in the figure of merit or the FOM for lamps, that is here. That is K atom steps per second, or when you go to a larger unit, you'll see M atom steps per second. It'll then give you kind of breakdown of MPI tasks here. And then another important point is that in order to make sure that your CPU processing isn't being throttled by the network, you want to look here. So in the case that you aren't using something that's like an HPC type network like EFA or like InfiniBand, this percentage will be much lower. It could be in the 60s, the 70s. When you see that it's 98% or higher, you know that you're using an HPC-like network. I say like because EFA is not technically HPC. Now, another metric you can look at is the total wall time. The total wall time will be lower with a better performance. And when you're doing something called strong scaling, so basically giving more resources to the problem, or adding nodes, for example, you basically want to see that total wall time go down. When you see the total wall time start to go up, you are no longer strong scaling. So as we remember, we had 2 pods. We had the lead broker that we just looked at. We also had the worker pod. They both are completed now, but the question comes up, what was the worker doing? Let's take a look. kubectl logs lamps flux node, 1 is the worker. And so this is going to be a similar output. Basically, they both get pointed at the same configuration file, but based on the host name in that configuration file, this node says, my host name is a worker, so I'm actually going to come up and bootstrap to the lead broker, connect the tree to the tree-based overlay network, which we call the T-bone or T-bon, if you will. And then I'm going to obviously run help with the simulation with MPI. And then when I'm done, I'm just going to exit with exit code 0. And that's why we see that the follower worker exited cleanly. Now we can delete our lamps train job. And we're done. Alrighty, let's switch our cluster to a little different resource type. What do you expect? Well, this is Kubeflow Trainer, so we need some GPUs. These are tiny GPUs because, well, you know, it's hard to get them these days. So these are the AWS G4DN extra large, kind of tiny, but very affordable, good for demos. They have the Tesla T4 GPUs. And so I basically just created this cluster, if you're curious, with this particular configuration here. Very simple, 2 nodes, and we just have workers. So let's take a look. kubectl get nodes. There they are. Alrighty, so we just installed the Kubeflow Trainer to our new cluster. Now let's take a look at the lamps train job that's going to use GPUs. So up here at the top, again, we have the runtime ref that is using the Flux runtime. But now for our tiny GPU nodes, we have 2 nodes with only 1 process per node. For the image, we're using a custom lamps build that has GPU. The executable, instead of just lamps, it's lamps GPUs. These are parameters specifically for Cocos. And once we get over here, for example, to V8, VY, and VZ, those are lamps parameters. And then the dash n, this is also for a lamps input. And then no cite, because says don't print the citation. Instead of EFA for our resources per node, we have limits and requests for what everyone's familiar with, one NVIDIA.com GPU, and we still have a few environment variables for MPI. And again, we're customizing the Flux view init. Let's create the lamps train drop. Get the pods, watch. The init container is going to be adding Flux. Pod initializing will pull the container. Don't worry, I've already pulled this very chunky container for us. We're running. So let's actually sneak into the container, specifically the lead broker, so the index 0. And we're going to make a bash that shell. And the reason is because I want to get a little look at the GPU devices. So let's do while true, do NVIDIA SMI fleet1 done. Alrighty, so we already see that the GPU is 100, 77, 84. We are using that little Tesla T4 GPU. Go, go, go. So I can't leave this open, but I wanted to show you. Now let's see if we can get out of this pod and get a look at lamps. So kubectl logs, and then we'll do lamps flux 0. So again, this is the lead broker. And what we're going to see is output for the GPU. It looks like we caught it. So again, we have some Python paths here. The command provided is much longer. This is a directive for software called Cocos that's going to help us use the GPUs. And this G here is actually saying a maximum of 2 GPUs per node because we actually only have 1 GPU per node. Here's the full command that is including Flux for GPUs. Oh, it just finished. Let's go back up. So importantly, this is saying 2 nodes, 2 tasks, 1 task per GPU, and then the lamps GPU command. So you see Cocos output here. Very similar output for lamps in terms of the simulation. Again, not as much CPU utilization because we're using the GPU, and MPI task breakdown. And again, the total wall time. So if we look here, we're going to be completed. If we look at the follower broker, the index 1, we're going to see a similar thing to last time that it ran and completed. So folks, that's it for today. That was lamps in 2 ways. First with the elastic fabric adapter or EFA, then with the Tesla T4, 1 GPU per node. By the way, AWS does have instance types that have both EFA and GPUs if you want the best of both worlds. Thank you so much for attending today. If you want to learn more about Flux, you can go to fluxframework.org or the GitHub organization of the same name. If you have a question for me, want to tell me what you're working on, or just want to say hello, you can reach out to me at socket1@llnl.gov.